Yes. Hello students, welcome to IMS Gate Academy. In today's session, we are going to do the concepts of mesh analysis. In the last session, I explained about nodal analysis, and also I explained different model problems also then. In today's session, I will give what is the mesh analysis, how that mesh equation is to be taken, and how to be done the problems that we can discuss today. Understand now. This is most expected concept of networks. So please try to attend the class up to ending. You will get the good information, I am sure. Understand now. Initially, you may find certain simple questions. Slowly, I will make the complex. Understand now. Every model question you will see. Yes, we can start then. Today, I would like to do mesh analysis. Mesh analysis. But directly we cannot enter into the mesh analysis. Initially, we should understand what is KVL. Voltage law is more important.
Hello. Hello. Audio video clear? Everyone please. Audio video clear? So audio and video clear? Please reply in the chat box. It is clear or not? Audio and video is clear? Audio and video clear? So okay, no problem. If there is any issue, please reply in the chat box. No problem. So this is your mass which is into the control room, and this is the mass which is exit from the control room. Okay.
starting कोई
Okay, so now it's video and audio clear? So it's audio and video clear? No, no. Okay, now it's okay. I think it's okay. Please reply in the chat box if it is all okay, audio and video clear, so that we will start the content part of that one. Okay, if it is okay, then we'll start the content part of that one. So if there is a mass of the fluid, this fluid itself has energy. What is the energy? Internal energy is the energy, internal energy, which is a strong function of temperature. So the fluid which is have some temperature, so it's have internal energy. This mass will into the system, so there is a motion. That means there is a velocity. This must have a velocity. Let's suppose v1 is the velocity, and there must be a velocity, and there must be a velocity, and there must be a potential energy. That means z1. This is the datum level. That means from here to some reference line. Let's suppose this is z1, and from here to a same reference line. Let's suppose this is your z2. So also there is a mass is out here, so it's have internal energy, exit kinetic energy, right, V2 plus potential energy Z2. Now we have to balance it. So what is the energy equation? Beta? Energy in minus energy out. This is the energy equation. Energy in minus energy out is equal to change in energy of the system. Now we assume that the system have a steady state. System have a steady state. That means the change in the property. That property is the energy is with respect to time is 0. That means rate of a change in the internal energy, kinetic energy, potential energy, etc. That is 0. That means what is that in the rate basis? That means what is the energy is in, the same energy is out. This is the energy equation in the steady state device. Okay, so what we can write here? We can easily write what, let's suppose in this system the heat will in, work will out. You can say like that. Yeah, in general, forget about all the things. In general, see the rate of energy transfer by heat, work and mass. Okay, this is okay. So rate of energy transfer in, that means this is your Q in. Rate of energy in the form of work, W dot in, no problem at all, plus due to the mass have an internal energy, so mass have an energy, all the form of, so this is mass M in, M into theta. Theta is the specific energy, and what is this in the form of? This theta is the specific energy of during the flowing mass. This is the flowing mass. What is that? Enthalpy plus kinetic energy per unit mass basis plus potential energy Gz. So this is the energy associated with the flowing fluid. This is the energy associated with the flowing fluid. What is the energy associated with the non-flowing fluid? So let's suppose a small e is equal to U plus V square by 2 plus Gz. This is the energy related to the non-flowing fluid, okay? And this is a flowing fluid. So this is theta, Mi. Similarly, we can write here at exit condition, what is that beta? Q out plus W out plus summation of all the outlet M dot theta. This is the simple things, nothing is the rocket science. So if we explain, okay, so if we write like that, that means we know that in the system heat added is positive and heat rejection is negative. So if you write Q in, minus Q out, okay, plus
all inlet section m dot, this is dot, theta is equal to W out is positive, W dot out, this is negative, minus W dot in, plus summation of all the exit m dot into theta. My dear, what is this? What is this? This is a net heat transfer. This is your net work transfer. So the net heat transfer, that means you can write like that, sir, net heat transfer, that means Q plus summation of all inlet m dot theta is equal to work, this is net work plus exit condition, outlet condition, m dot theta. This is your energy balance, that means energy equation, first law of thermodynamics for a steady device. First law of thermodynamics for a steady device, okay? So now if you explain this one, so this is a rate basis, beta, mind it, this is a rate basis. That means rate of heat transfer, this is net, plus summation of all inlet m dot, what is theta? H plus V square by 2 plus Z Z is equal to W dot plus summation of exit, okay, summation of exit condition, that means exit into M H plus V square by 2 plus Z. Dear student, there is a one catch is that. What is that? What is that? Okay, so is there any? Okay, 1 second. Comment can't. Okay, yes. Now it's okay. Okay, Atul, okay, yes, yes, yes. So this is what m dot. Okay, so this is your m dot. Now, my dear. Now, my dear. C is not working. So if there is a one inlet, one exit, and there is one inlet, one exit. Yes, yes, Atul. I will cover all the unsteady problem also. Today we will discuss steady, and little bit I give the concept of unsteady, and tomorrow, next session, we will start the unsteady problem also. Okay? So this is mainly, so what is that? Energy in minus energy out is equal to energy out. Okay? So if there is a single inlet, so Q dot plus single M1I inlet HI plus VI square by 2 plus Z ZI W dot plus M dot E HE plus VE square by 2 plus G ZE. Okay? Okay? ऐसे ऑन करो यार, नहीं ऑन है, इसको निकाल कर भी फेंक दूँगा मैं, निकाल कर भी फेंक दूँगा, ऑन नहीं है, फिर फेंक दूँगा। अरे कहाँ ऑन है? हाँ अभी ऑन हुआ, नहीं। Okay? Now, so this is okay. So in general, there is a single. Now, so this is your precisely. Beta, maximum in the steady flow condition, what is that? We can neglect. This is must be that. This is must be that. In 99%, the 99% we have to neglect it. The change in potential energy is negligible. This is strong assumptions, but sometime kinetic energy is here. So what do you have to write? You write Q dot plus Mi HI plus VI square by 2 is equal to W dot plus ME HE plus. That's it. This is our mini question. Now we will start the problem. Now we will start the problem. What is that? See this one, beta. Just read this question. Just read this question, beta. Just read this question. What is that? Just read this question. A compressor of a large gas turbine. See, in the power plant, we have studied two types of a turbine. Working fluid. One is the phase changing fluid. Other is the single phase fluid. Single phase fluid working on a cycle that is called Breton cycle, and that Breton cycle works on Breton cycle, and that Breton cycle is what? Gas power plant. Okay. So in the Breton cycle, we use the compressor to increase the pressure from the inlet to exit, and when there is a, here it is written as the pump of a large steam turbine. So if there is a steam turbine, there must be a pump. So pump we will use in the Rankine cycle, and compressor we will use in the Breton cycle. So it is the Breton cycle. So in this Breton cycle, the most important assumption is that what is the fluid is in the cycle, in the process, that fluid doesn't change its phase. That fluid doesn't change its phase. Okay. So in the gas turbine, the fluid have a single phase. Fluid have a single phase. Okay. Receive air from the ambient. That means the compressor is receive air. That means inlet. What is the inlet? Inlet is from the ambient. In general, you can think the compressor inlet is from the ambient. This is very important, along with the assumption also. So compressor inlet in general, it is ambient. Okay. But the pump inlet is the exit of the condenser. If there is a Rankine cycle is there, so there is a pump, and pump inlet is the exit from the condenser. But in general, the gas turbine, the compressor inlet is at the atmospheric condition. This is very important. Okay. At what pressure? It will, that means it will take the fluid from the atmospheric pressure, atmospheric condition. And what is the atmospheric condition? 95 kilopascal. And at this is, see, this is 20 degrees centigrade in general. With a low velocity, that means inlet velocity we can neglect. Now, at the compressor discharge, that means this is the exit condition. This is your exit condition. Air exit at 1.252 megapascal. This is very important. So, my dear, see the difference of the pressure level. The inlet is in 95 kilopascal and it is 1.52 megapascal. Such a tremendous high pressure will be developed with the help of compressor. Okay. And along with, if you increase the pressure, if there is a single phase fluid, the temperature also increase. Okay. With a velocity, that means, see my dear, the exit velocity is considerable, but the inlet velocity we cannot be considered much more. Why? Because if you pressurize any fluid from very low pressure to high pressure, obviously the exit velocity will exist. The exit velocity will exist. Why? Because we have to change the pressure from low pressure to very high pressure. So the change in pressure is responsible. The change in pressure is responsible to increase its velocity. The change in pressure is responsible to increase its velocity. Okay. The power input, that means what is the power consumption to the compressor? So the power input, it is given the compressor input power. That means this is an input device. Compressor is a kind of input device. Pump is a kind of input device. So it will consume the power 5000 kilowatt. Okay. Determine the mass flow rate of air through this unit. That means we have to find what is the mass flow rate of the air. That's it. So let's start with the question. Okay. Solution. What is that? See beta. This is your compressor. So this is your compressor, no doubt. Okay, no problem. So we have to draw like that, no problem. So there is a compressor, and compressor is a compressor, that means it will compress. So compressor, during the compressor, pressure will increase. Pressure will increase. So pressure will increase, velocity will decrease. Pressure will increase, velocity will decrease. No, that is wrong. That means the minimum area, velocity also increase. Pressure will increase, also the velocity will increase. That means we have to discharge the air through a minimum area. That means this is your compressor. Let's suppose beta, this is your compressor. Okay. Let's suppose this is your compressor. This is your compressor. Okay. This is your compressor. No problem at all. Now, this is your compressor, and it will compress from inlet. This is your inlet section. Let's suppose this is your inlet section. This is your inlet section, and this is your exit section. Okay. This is your inlet section, and this is your exit section. That means this is your I, and this is your E. This is your section. This is your inlet section, and we assume this is our control volume. We assume this is our control volume, and in this one there is air. Now it will in and exit. So this is a in and this is out. And the condition is given. Condition it is given with a, what is the condition given? What is the condition given? What is the fluid? Fluid is your air. What is the fluid? Fluid is your air. Okay. Fluid is your air. Or what is the condition? It is the inlet pressure is 95 kilopascal. It is given in the question. Inlet temperature is 20 degrees centigrade. That means it is at atmospheric condition. Exit pressure is very high. That means 1.52 megapascal. Okay. Exit temperature it is given 430 degrees centigrade. Exit velocity it is given 90 meter per second. And also work in it is given. Work in power. So W it is minus 5,000 watt. Okay. So we have to find mass flow rate of air. Okay. So start with the steady flow energy equation. Steady flow energy equation. What is that beta? Heat transfer Q dot plus M Q dot plus M1 MI HI plus VI square by 2 plus ZI is equal to W dot plus M dot E HE plus VE square by 2 plus ZE. Now, my dear, same horizontal level, that means it is not very long. So, the potential datum is negligible. The inlet velocity is negligible. Okay. And see, my dear, in the question it is not given the what is the condition of heat transfer. So, my dear, see the compressor it is a more and more work input device. So, with in the comparison between the work input and heat addition, this is the net heat transfer and this is net work transfer. So if you compare with these two, the net work transfer is much more than the net heat transfer during the compression process. So you can neglect it. This is the very good assumption. That means you have to adiabatic device. Okay? You define for the adiabatic. So what is that? Your final. What is that? That means, and this is your mass inlet is same as the mass exit. That means MI. What is mass in? Is the same mass is exit, which is equal to M. You can write like that. So what is the required condition? MHI, no problem at all, okay, is equal to m dot, this is m dot, into HE plus VE square by 2 plus W dot, okay, W dot is there. Now you have to divide this mass, that means W dot by m dot is what, beta? HI minus HE minus VE square by 2, no problem at all. Now see this one, this is in which unit? This is in which unit? See beta, this, see this W dot, that means if you write like that, W dot, this is your kilowatt. Let's suppose this is your kilowatt. It is given in kilowatt, okay? And this is your kg per second. So this is your kg, this is what, beta? This is your kilojoule per second divided by kg per second. This second cancel. So this is what? Kilojoule per kg. This is your kilojoule per kg. So enthalpy, it is also in kilojoule per kg. H is also kilojoule per kg. But this is your meter square per second square. So this is your meter, that means this is your kinetic energy, it is in joule. This is your kilo, not a kilojoule. This is your joule. This is your kilojoule per kg. This is your kilojoule per kg. So this is your kilojoule per kg, and this is also kilojoule per kg. Kilojoule per kg. But this is your joule per kg. So how to make kilojoule per kg? You just multiply with this one. That means W dot by M dot is equal to HI minus HE minus VE square divided by 2 into 1000, very important. Then it is, the unit is balanced. Yes, what is that? Sir, 3 year means 3 year. Yes, आदेश, वेरी इंपॉर्टेंट सर 3 ईयर में, 3rd ईयर में हूँ, हीट ट्रांसफर कॉलेज में स्टार्ट हुआ है आज, क्या सेंजल एंड आरके राजपूत बुक सही है क्या? यस, वेरी गुड सजेशन, वेरी गुड हुआ, जो आपको ये बताया है, जिसने आपको बताया है, वेरी गुड. सेंजल यू गो टू द थ्योरी पार्ट, सेंजल यू गो टू द थ्योरी पार्ट, एंड आरके राजपूत यू गो टू द problem. So R.K. Rajput, the problem of standard of the problem is very good, and there are many problems is there. So according practice point of view, the R.K. Rajput is very important, and for the practical implication, practical understanding, the Senjal is very good. Thank you. Okay. Anyone? Or this? Okay, beta? Clear? If you have any problem, then please start. Okay? There is a heat transfer also lecture is going on. Okay? That is very good. Now, so this is your, okay? Now, my dear, see here we have as an ideal gas, so you can take that one, Cp Ti minus Te. You can write like that. Okay? So what is the Cp of the air? You can take this one, 1.004 kilojoule per kg Kelvin. This is your Cp, okay? And Ti you have Te, put this value, and you have Ve, put this value. What is this? So from here you can easily calculate mass flow rate from this equation. Put all this value. You put here negative sign. So minus, this is your 5,000 divided by m dot. So you can take m dot, no problem. M dot is equal to, you all put this value 1.004 into 20 minus, this is 20 minus 430, 430, okay? Minus, again you have to put minus, what is the velocity? Exit velocity? Exit velocity 90. So 90 square divided by, this one 90 square divided by 2 into 1000. Now you have to solve and you can get the mass flow rate. If you solve this one, the mass flow rate, it is your 12 kg per second. This is the mass flow rate of air. Oh, okay. Sir, I prepare fluid mechanics and hydraulic machine by R.K. Rajput book. Is this book is sufficient for the GATE mechanical engineering? See, beta, if you prepare the fluid mechanics and hydraulics, yes, R.K. Rajput in general it is very good. This is that is sufficient. But if you find very good standard question, that means very good presentation and the vector approach, you go through the S.K. Som book, okay? S.K. Som and Suman Chakravarti. S.K. Som and Suman Chakravarti. Suman Chakravarti. S.K. Som and Suman Chakravarti. This is the best book for the mechanical engineering. Okay? So, yes, R.K. Rajput is very good, no problem. But the R.K. Rajput, the fluid mechanics have a not that much level of the feeling. If you go through the feeling of the fluid mechanics, that means what is the presentation in the S.K. Som, and also the problem is very, very intelligent. And in this book, sometime directly question, that means little bit change in numerical value, the question is came in the GATE examination, okay? So I hope you understand. Now next question, Ardari, if you have any problem, okay? Now, this is good. This is good. Okay. So we have to take next problem. This is your next problem, okay? Just see this one. Just see this one. This is your next problem. What is that? Superheated vapor ammonia. Superheated vapor ammonia. That means the ammonia, there is a ammonia that is a superheated, okay? Superheated vapor ammonia, okay? So there is a superheated vapor. Superheated vapor, okay? This is superheated vapor. What is the superheated vapor? Okay, sir. Sir, I prepare strength of material by only R.K. Rajput. Oh no, R.K. Rajput is not good, okay? Theory of machine by R.S. Khurmi. Machine design by R.S. Khurmi. V. Bandari, machine design. Plus design data book. Power plant engineering from P.K. Nag. IC engine gas turbine by the V. Ganesan. Yes. Little bit it is very good, no problem. Combination is very good. If you follow that standard, there is no any problem. In my suggestion, if you know that what is the best book, there is one separate video is there in which we have to cover all type of the book. See, if you go to the basics thermodynamics, P.K. Nag is there. Advanced application thermodynamics, V. Ganesan, it is very good. Okay. Number second, fluid mechanics, S.K. Som is very good. For the turbo machinery, also S.K. Som is very good. Okay. Hydraulic machine is S.K. Som. Yes. Little bit feel difficult. Why you feel difficult? If you understand the R.K. Rajput, you don't feel the difficulty. Why you are feeling the difficulty? Please tell me. I give you one suggestion. Why you are feeling the difficulty? Why? Because you don't know the vector. You don't know the vector approach. That's why you have a feel difficulty. And R.K. Rajput is very simple. No. Turbo machinery is also very good for the S.K. Som. S.K. Som is the very good book. Like that, P.K. Nag is for the basics thermodynamics is very good. Okay, that books these type of books are very important book. Okay, heat transfer, Senjal and R.K. Rajput, very good. Okay. Dom Kundwar, very good. Dom Kundwar is very good, beta. Dom Kundwar, it is good. Okay, no problem. You can follow that one. Okay. Now, superheated vapor of ammonia enter the insulated nozzle. This is a nozzle, and this nozzle is insulated. That means there is no chance of heat transfer. It is given. This is insulated. That means there is no chance of heat transfer. Insulated. Heat transfer is 0. Okay. Now, and see, superheated ammonia enters. So this entry is superheated. Heated ammonia. at 20 degrees centigrade and 800 kilopascal. That means very low temperature and very high pressure, 800 kilopascal. This is superheated condition. This is your superheated condition, okay? Now, as shown in figure, with a low velocity, that means entry velocity we have to neglect it, okay? And the steady rate, that means the flow rate, mass flow rate, it is given 0.01 kg per second. The ammonia exists at 300 kilopascal with a velocity 450 meter per second. The ammonia exit, that means it will exit condition. Ammonia exits at, see, this is the nozzle now. So what is the function of the nozzle? The function of the nozzle is to increase the velocity, that means increase the kinetic energy. Where from the kinetic energy will get? From the expansion of the pressure. So the pressure will reduce. See this one, beta. Initial pressure, entry pressure at the nozzle is 800. Now exit pressure is 300. So the pressure will reduce, and that reduced pressure will be responsible to increase its kinetic energy. That reduced pressure will be responsible to increase its kinetic energy at the exit condition. Okay. Determine the temperature. Determine the temperature or the quality if the saturation. You have to find the also quality. That means you have to find the exit condition. Where is the exit condition? Okay. And the exit area of the nozzle. And the exit area of the nozzle. That means you have to find T exit. You have to find S exit. You have to find area at exit. This much. Okay. Okay, now we have to start this one. What is that? This will be a little bit good problem. So, start. So, this is your nozzle. Okay, same nozzle. This is your nozzle. Okay. This is your nozzle. This is inlet condition, and this is exit condition. This is our control volume. This is our control volume. This is in and this is exit. Okay. There is no heat transfer. There is no heat transfer. It is given adiabatic, no heat transfer in or exit. Okay. And nozzle also there is no any working device. The work transfer is 0. Nozzle only responsible to increase the kinetic energy at the exit. Okay. So what is the given here? Ammonia. What is that? Ammonia it is. Okay. Ammonia. Ammonia. NH3. Ammonia. Fluid is ammonia. And what is the given? In temperature at inlet is 20 degrees centigrade. And pressure at inlet is 800 kilopascal. Okay. And also it is given velocity at inlet is equal to 0. This is inlet condition. Exit condition. Exit condition, P exit, it is there. What is that? 300 kilopascal, it is given. And V exit, it is given 450 meter per second. Okay, 450 meter per second. Okay. Okay. So we apply the steady flow energy equation first. Q. Steady flow energy equation. Yes. Q is equal to Q plus single inlet, single exit, M dot HI plus VI square by 2 plus ZZI work transfer plus M dot HE plus VE square by 2 plus G ZE. Now, my dear, there is no any change in potential energy. So, the potential energy change we can neglect. Okay. Now, the inlet kinetic energy is also 0. Only exit is there. There is no any heat transfer. Adiabatic. There is no any work transfer. There is no any working device. It is still okay. Right. So Ardari said that, sir, exact solution of the Navier-Stokes equation. This is the classes of the thermodynamics beta. Navier-Stokes equation, you can read in fluid mechanics. Our previous lecture is there, available in the fluid mechanics. So you can go and watch Navier-Stokes equation, okay? That is the very good equation. If you feel that, what is the Navier equation? Navier equation is the force equation. Force equation. In the fluid mechanics beta, there are three equations is there. First is the conservation of mass. Second is the conservation of momentum. Third one is the conservation of energy. Conservation of mass gives the continuity equation. Conservation of momentum gives the Euler's equation and Navier-Stokes equation. And conservation of energy gives the Bernoulli's equation. There are three conservation in the fluid mechanics. First is the mass conservation, second is the momentum conservation, third is the energy conservation. Mass conservation, continuity equation, momentum conservation, Euler's equation and Navier-Stokes equation, and conservation of energy is the Bernoulli's equation. Now, conservation of momentum, we apply two types of fluid. First is your inviscid fluid, and second one is the viscous fluid. So, conservation of momentum, if you apply the inviscid fluid, that equation will be finally will be obtained by obtain Euler equation, and if the fluid is viscous, the final equation is Navier-Stokes equation. So Navier-Stokes equation is the force equation in which the fluid we consider we have a viscous fluid. If that means in a viscous fluid, if you apply the force equation, the final outcome is the Navier-Stokes equation. If there is an inviscid fluid and if apply the momentum equation, exact solution for Navier-Stokes equation. Which one? Steady flow energy equation. This is a steady flow energy. What? There is no any Navier-Stokes equation. Okay. Now, so this is the not a Navier-Stokes equation. This is a steady flow energy equation. M dot Hi. I think you are not interested to studies. M dot He plus VE square by 2. Okay. How can you say that, beta? No, steady flow energy equation and Bernoulli's equation outcome from the Euler equation. No, that is no outcome. See, if you have a mass, you move it, you have a momentum, m into v, rate of change of momentum, dv by dt. If you integrate it, then there is energy. So energy is nothing. Energy is the integral form of the momentum equation. So steady flow energy equation is the energy equation. It is not a momentum equation. This is the energy equation. So a steady flow energy equation is the energy equation. Bernoulli's equation is also energy equation. How to derive? It is not derived by the Euler's equation. But this is not derived by the Euler's equation. This is simply conservation of energy. Bernoulli's equation is derived from the integral form of the momentum equation. So there are two things which is very clear. So steady flow energy equation and Bernoulli's equation. See, what is the similarity between these two? I will just tell you. This is a good question. These both are applicable at a cross section. See, this Bernoulli's equation is applicable at a point. Bernoulli's equation is applicable. Number first, both are the conservation of energy. Both are the energy equation. Energy equation. This is also energy equation. Okay? But what is the main difference? The main difference is that steady flow energy equation is apply at cross section. And this energy equation will apply at at the point, between the points, yeah, at the point for single stream. Okay, and this is your cross section. That means, and what is the energy equation? Is this one? The energy equation is this is your energy equation is, if you apply the energy equation, that means energy in is equal to energy out. In this one, you can integrate integral form of Euler's equation. So this is the integral form of Euler's equation. So steady flow is simply conservation of energy. This is also conservation of energy. But the Bernoulli's equation is, this is also conservation. This is also energy equation. This is also energy equation. Both are the energy equation. But the Bernoulli's equation will come out from the integral form of the Euler equation. That means the Bernoulli's equation, it is an energy equation which is the integral form of the Euler equation. That means if you have a Euler's equation, you can just integrate between the 2 points. Here you have an energy equation, and if you want to integrate, we can integrate between the 2 cross section, inlet and exit. That means if you denote in this one, we have to denote I inlet and E for exit. In this one, we have to denote 1 point at one location and second point at another location. So 1 and 2 we have to denote, and here I and E are denoted. It is clear? Now it is clear? Now it is clear, beta? Steady flow energy is the first law for thermal. Yes, now it is good. This is your first law for control volume system. Yes. Understand, sir. Great. This is very important slide, okay? Now, so we have to go through that. So it is this one. Now, so what is that with our HE is equal to HE, okay na? So what is that? HE is equal to HI, there is a minus, I think, na? So HE, so HI minus V square upon 2. So my dear, from here, HI, where we have to find the HI? So from this pressure and temperature condition, it is given, na? There are 2 points it is given. Temperature and pressure it is given. So according to that temperature and pressure, we have to find HI. Where? From ammonia table, from NH3 table, or in the exam given, it is given. So you have HI, you have a velocity. So if you calculate this one, so there is HI minus VE square must be 2 into 1000 is there. Otherwise you have to mistake. So what is exit enthalpy? The exit enthalpy is you have to just calculate. So exit enthalpy, okay? So you have to calculate the exit enthalpy. Now, but we don't know what is the condition of the exit enthalpy. But we don't know what is the condition. That means this exit enthalpy we have, inlet enthalpy we have. Exit enthalpy, inlet enthalpy. But what is the condition we don't know. What is the condition we don't know. So we assume for that one, for the sake, this is the important thing. So how to start? We assume the exit in a wet region. We assume like that, okay? So what is that? Assume that it is 2-phase region. Exit, that means outlet, you can take outlet. Out at 2-phase region. that means weight. And if there is a weight, so we have a dryness fraction. So what is H2 beta? If H2 is what? HF plus X2 HFG. Yes or no? Now at this, it's which condition? This is at what condition beta? This is at what condition? H2. See, this is at this pressure. 100 kilopascal, 300 kilopascal. So at a 300 kilopascal, we have, if you have, that means you can find this is at 300 kilopascal. So at a 300 kilopascal, you have to read this value, HF and HFG. So you find at a 300 kilo from ammonia table, from NS3 table. So if you have at a 300 kilopascal, you have HF, HG, and you already calculate H2. So from here, if you find X2, so the X2 is 0.947, and this is in between 0 to 1. This is in between 0 to 1. So exit is a dry saturated condition. Dry saturated condition, that means wet region. Okay, wet region. This is your wet region. Now, this is your wet dryness fraction. Okay. Now we have to find the exit area. So what is that? Mass flow rate is density at exit, area is the exit, velocity at the exit. We know that, and we have know that area at the exit, velocity at exit divided by the specific volume at the exit. Why? Because we have density, and density is equal to inversely proportional to a specific volume. So put that specific volume. Now the exit is at in wet region. Why? Because this have a dryness fraction. So we have AE, VE, and what is the VE? VE is VF plus XE, VFG, and this is at which pressure? This is at 300 kilopascal. So at a 300 kilopascal, you know this one. So, and you know this mass flow rate. How much? 0.01. Area exit. Velocity is what? 450 at exit divided by this value. You know this one. Calculate this one. So from here, you can easily calculate the exit area, and exit area is 8.56 cross 10 to the power minus 6 meter square. Thank you. Okay. So I hope you are, this is the question related to the exit condition at a dry saturated condition, that means in a wet region. Dry saturated, that means in a wet region. And what is the area? So if we don't know what is the exit condition, simply you find the dryness fraction. If you have a dryness fraction in between 0 to 1, there must be a wet region. So for the wet region, the calculation are in this basis. That means if you calculate the enthalpy, HF plus X HFG. If you calculate the specific volume, VF plus X VFG. If you calculate the entropy, SF plus X SFG. Okay, like that we have to calculate all the things. Okay, so is there any problem? We have to take other problem, but there is a less. The timing is not available for me, so that we are now stop here. So today we will discuss the steady flow energy equation. Some question, good question. Now in the next session we have to start. We have to start the unsteady flow problem. Okay, so unsteady flow problem, charging, discharging of a tank, we'll have to discuss with the sum problem. Okay, after that we have to go through the entropy, then there is a exergy, and then there is a some portion of a vapor compression refrigeration cycle. Okay, so these are the first module in which we have covered all the things for the 1 hour. Okay, so my dear, thank you, bye bye.